Hello everyone, it's 1 p.m. Eastern Time, and that means it's time to begin another of our monthly CoCoRaHS WxTalk webinars. Thanks for joining us today. I'm your host, Henry Regis, and along with me is my co-host, state climatologist for Colorado and founder of CoCoRaHS, Nolan Duskin. Behind the scenes today, running our program, are Zach Schwalbe and Noah Newman, and we're coming to you live from the Colorado Climate Center here in sunny Fort Collins, Colorado, at the Colorado State University campus. And it's a cool morning out here. It was in the 40s, upper 40s earlier on. So a delightful day here in Colorado. Hey, for those of you who are unable to join us for our live broadcast today, we'll be recording it for future viewing on our website. And all of our WxTalk webinars are sponsored by grants from NOAA's Office of Education and the National Science Foundation. Well, today's webinar, we're going to discuss the methodology behind Colorado State University's seasonal forecasts for hurricanes. You've most likely heard these over the news over the years. We'll be looking at new techniques for issuing 2-week forecasts. Caribbean basin forecasts will be examined. And finally, the causes of observed multi-decadal variability in Atlantic basin hurricane activity will be talked about. Wow, this webinar is chock full of great stuff. And who better to present it than an old friend of ours, Phil Klotzbach. And Phil is a native of Plymouth, Massachusetts, a good friend of CoCoRaHS and the Climate Center. Phil is a research scientist here in the Department of Atmospheric Sciences at Colorado State University, where for the past 11 years he's been the co-author on the Atlantic Basin hurricane forecasts with Dr. Bill Gray. Dr. Gray, originally scheduled to be with us today, unfortunately he has a prior engagement and unable to join us, but Phil will do a great job as they team together on many of these things. Phil first became the first author of the seasonal hurricane forecasts back in 2006. And besides tropical cyclones, Phil's other research interests include climate change and nor'easters. Well, after receiving his master's degree in 2002, get this, Phil thru-hiked the Appalachian Trail from Georgia to Maine. That's no small task, 2,100 miles. He's also climbed all 54 14,000-foot peaks in Colorado. He's completed 7 marathons and 3 ultramarathons. Wow, Phil sounds like a real couch potato. Phil, welcome. Glad to have you with us today, and it's a pleasure to have you on our show.
Well, thank you very much, Henry, for the very nice introduction, and I'd like to thank all of you for listening to today's presentation. So let's begin. Let's see, here we go. All right, ready to rock and roll. So yeah, we're going to talk with you today about Atlantic Basin seasonal hurricane prediction. Basically, I'm going to go through a few of the major things, and we're going to obviously spend a little bit of time even talking a bit about what we are currently seeing in the Atlantic. Obviously, we had a new tropical storm this morning. Tropical Storm Aaron has just formed in the far eastern Atlantic out by the Cape Verde Islands. So we'll talk a little bit about that, as well as the disturbed area near the Yucatan Peninsula that could potentially impact the central Gulf of Mexico later this week. So basically, the actual outline of this talk is I'm going to begin with an introduction, basically discussing the methodology that we use to issue our Atlantic Basin seasonal hurricane forecasts. I'll then spend some time talking about multi-decadal variability in the Atlantic Basin. Basically, the Atlantic Basin goes through active periods of about 25 to 35 years, and then similar length periods of 25 to 35 years characterized by fewer tropical cyclones. And I'll talk a little bit about that, and we've been in this active era since 1995. So we'll talk a little bit about how much longer we expect this active period to last. We'll then talk about the verification of 2012, which was an interesting season. It was characterized by many tropical cyclones. We had a total of 19 storms in 2012, but only 2 major hurricanes, and those 2 major hurricanes only lasted a total of 6 hours each. So not quite as, while we had a lot of storms, they weren't very, very intense. Obviously, I'll talk a little about Hurricane Sandy, which was kind of an unusual hybrid storm. Obviously, did a huge amount of damage, but wasn't actually technically a tropical cyclone when it made landfall in New Jersey. We'll then spend some time talking about the 2013 Atlantic Basin hurricane season, and we'll finish with our discussion of the 2-week forecasts. We actually put out our last 2-week forecast on Friday, August the 2nd, and we will be putting out our next 2-week forecast actually tomorrow, and I'll talk a little bit kind of what we're looking at for the next 2 weeks. So let's talk first about how we do what we do at Colorado State. And I like to start with a quote from the great Yogi Berra, who was a catcher for the New York Yankees back in the 1950s. And he once stated that it's tough to make predictions, especially about the future. And we would certainly agree with Yogi that obviously issuing forecasts is a real challenge. Obviously, there's a lot you have to do to come up with the best forecast that you can. Now, one challenge that you have when issuing a seasonal forecast as opposed to a day-to-day weather forecast is that if you are issuing a seasonal forecast, or if you're issuing a day-to-day weather forecast, what happens is you issue a forecast, and if it's a bad forecast, people may give you a hard time. However, after that, after a few days or whatever, people forget about that as you're constantly making new forecasts. But if you make a bad seasonal forecast, people give you a hard time about it for an entire year. So all the more motivation that we have to issue the best forecasts that we can. And this next statement by Yogi Berra really kind of helps summarize the methodology that we use, and that's that you can see a lot by looking. Basically, what we do is we use a historical perspective and we use statistical modeling. We don't wake up in the morning like these guys and see if we can see our shadow, unlike what some of our critics might say. Basically, what you can do is you go back into the past, and we know which years in the past were active hurricane seasons, and we know which years in the past were inactive hurricane seasons. Then what we do is you can go and look at these active seasons and see what precursor signals were there. That is, what conditions were present in the atmosphere and in the ocean prior to active seasons in the past, and alternatively, which conditions were present in the atmosphere and in the ocean before inactive seasons in the past. And what you'll find is that in general, you tend to have recurring sets of conditions. One set before active seasons and a different set before inactive seasons. Before the mid-1980s, when Dr. Gray started issuing these forecasts, there really was no way to know whether the upcoming season was likely to have above or below average hurricane activity. What Dr. Gray noted in the early 1980s is that when you had El Nino conditions in the tropical Pacific, you tended to have fewer storms in the Atlantic. Now, El Nino conditions, what those involve are abnormally warm water in the eastern and central tropical Pacific. When you have this abnormally warm water, what that tends to do is it increases upper-level winds out of the west in the Atlantic. Now, in the tropical Atlantic, your upper-level winds blow out of the west typically, and your low-level winds are the trade winds, the winds that blew the explorers over to the New World, and those blow out of the east. So if you think about this in the vertical, you have easterly winds at low levels, westerly winds at upper levels, and you have a shear in the vertical. Now, unlike tornadoes, hurricanes thrive in areas of very light vertical shear, and consequently, too much vertical shear tears apart developing tropical cyclones. Typically, when you have El Nino conditions, you see more vertical shear. So this is one of the predictors that was utilized in the early 1980s forecast schemes that Colorado State University issued, and we continue to use El Nino as one of our primary predictors now, along with a whole pile of other predictors, which I'll go into detail describing when we get into a more thorough discussion of the forecast model itself. This is just a contrast to our forecast from numerical prediction. Numerical prediction involves going back into, or basically not going back into the past, just taking your conditions at an initial time and integrating them forward in time. And this is the way you use numerical models, and these forecasts work out very well, say out to about 5 to 10 days, when your atmospheric momentum fields are the dominant factor. However, after that point, you have to start taking into account lots of complicated relationships between the atmosphere, the ocean, and the land surface. And if you can't adequately take into account all these complicated relationships, your forecast degrades towards chaos. So when you're issuing forecasts, say, for the hurricane season months in advance, in general, statistical prediction techniques work out reasonably well. There are some numerical techniques that are starting to work with statistical or with seasonal hurricane prediction, but these primarily use ocean surface conditions as their primary forcing, since the ocean has a lot more memory and a lot more persistence from day to day than does the atmosphere. This just shows all the complicated relationships that you would have to take into account to adequately model the climate more than, say, 5 to 10 days in advance. And certainly if you look at, say, day-to-day weather prediction, in general the models show significant skill, say, out to about 5 to 10 days. After about 10 days, you start to find that your forecast really deviates significantly from reality, and that's just because there's uncertainties in the initial conditions, there's uncertainties in the model, there's approximations that are made, and eventually these degrade your forecast towards chaos. So consequently, we use a statistical modeling approach to come up with our forecasts at Colorado State University. So now, before we get in and talk about the 2012 hurricane season and then obviously the current season, I want to talk with you some about multi-decadal variability in the Atlantic Basin. You may have heard it discussed as the Atlantic Multi-Decadal Oscillation, or the AMO, and as well as we refer to fluctuations in strength of a large-scale phenomenon known as a thermohaline circulation. And I'll talk a little bit about this as we move in and talk in more detail about this multi-decadal variability. You can see significant multi-decadal variability in the Atlantic Basin. For example, from 1945 to 1969, we had 80 major hurricanes in 25 years. So that's averaging a little bit over 3 major hurricanes per year. And major hurricanes are the ones that we care about the most, because even though when you look at them, they only are about a quarter of all the systems that form in the Atlantic Basin, when you take these systems and normalize them by population, inflation, and wealth per capita, they do about 80 to 85% of the damage. So from 45 to 69, we had a significant number of major hurricanes. Then in the next 25 years, we had a much reduced number of major hurricanes. We only had 38 major hurricanes during 25 years, so a significant reduction from what we had during the previous 25 years. Now, from 1970 to 1994, obviously during that time period, we tended to have a lot of people moving to the coastline. And that's because during that time, air conditioning became affordable, so a lot of people moved to the coast during a time when we had many fewer major hurricanes. And then, unfortunately, we've been in a more active period since 1995, the last 18 years. We've had 66 major hurricanes, or if you were to take that and normalize it to 25 years, 92. So we've been in a very active period since the middle 1990s. And this is either referred to as a positive phase of the Atlantic multi-decadal oscillation. Alternatively, we believe it's also at a time when the thermohaline circulation is strong. And I'll talk a little bit more about the thermohaline circulation in a minute. Basically, the thermohaline circulation is driven by two primary components. The thermo component, which is your temperature component, and then your haline component, which is your salinity component. And the thermohaline circulation primarily is restricted to the Atlantic Basin, and that's due to the fact that we have higher salinity content values in this basin. For example, if you look in the Atlantic, you can see the green colors in the subtropical Atlantic, and what this indicates is that you have higher salinity content water there. So the Atlantic has higher salinity content than the Pacific just because primarily you don't get mixing through the Isthmus of Panama. Since that filled in a few million years ago, you don't get mixing there, and consequently the waters tend to be a little more saline in the Atlantic than they are in the Pacific. Also in the Atlantic Ocean, you tend to have slightly stronger subtropical highs. And with these stronger subtropical highs, you have more evaporation than precipitation, and consequently your salinity builds up. So obviously you can see the differences here aren't particularly strong, but only a few percent differences in salinity content can make a difference between whether you get a deep water formation occurring or not. Basically, deep water formation occurs in the Atlantic Basin because you have higher salinity content waters there, both at the surface as well as all the way down to 500 meters. So you have this higher salinity water, and it moves to the north in ocean currents such as the Gulf Stream and in the North Atlantic Current. When the thermohaline circulation is strong, you have lots of warm, salty water moving into the far North Atlantic. When it reaches the far North Atlantic, what occurs is that you have this warm, salty water that cools, and cold, salty water is very dense and can sink to deep levels in the ocean in a process that's known as deep water formation. This deep water formation process is localized near the coast of Greenland, and you get sinking of water there, and then you have a return flow at deep levels back towards the tropics. Now, when you have the thermohaline circulation strong, you get less of a return flow along the west coast of Africa, and consequently you have less of a northward currents off of Africa, and the Atlantic begins to cool. Alternatively, when the circulation is weak, you get less warm water sinking and you get more of a return flow out of the north along the west coast of Africa. Consequently, the waters in the tropical Atlantic begin to cool, and overall you just get a cooler, more stable atmosphere in the tropical Atlantic. So that's really why this thermohaline circulation, we feel, impacts tropical cyclones in the Atlantic, is due to the fact that it then alters water temperatures in the tropical Atlantic. And that's how you start impacting overall basin-wide activity in the Atlantic basin. Now, unfortunately, we don't have great salinity data going back very far, but what we have going back quite far is sea surface temperature data. And using the marginal salinity data that we do have, we can show that the salinity and the temperature data correlates quite well going back to 1958. You can see in general, when the water temperatures are warm, your salinity content is high. Alternatively, when your water temperatures are cool, your salinity temperature, or when your water temperatures are cool, your salinity tends to be lower. So you can see how these fluctuate on these multi-decadal timescales. Warm water, higher salinity; cool water, lower salinity. So what we do is, and since we don't have good salinity data going back very far, we use sea surface temperature anomalies as a proxy. If you use this as a proxy, you can use this and take it all the way back to the late 19th century. And when you have warm waters in the far North Atlantic, you can see when you have warm waters there, you tend to get warm waters also in the tropical Atlantic, as well as you tend to see cool waters in the eastern and central tropical Pacific. What that does is that implies that you have warm water in the tropical Atlantic, meaning more fuel for developing tropical cyclones. Cooler water in the tropical Pacific means that you tend to have La Nina, more La Nina-like conditions there, which again, overall, is associated with reduced vertical shear that we talked about earlier, and overall conditions that are more conducive for an active season. So you can see this multi-decadal variability that extends all the way back into the late 19th century. Warm in the latter part of the 19th century, cold from around 1900 to 25, warm from the mid-20s to the mid to late 1960s, cold from 70 to 94, and then warm since around 1995. Obviously, one of the big questions is, well, how much longer will this active period last? How much longer will this active period last? We've been going through this active period for nearly 20 years. You would expect maybe about another 10 to 15 years of generally more active seasons, and then we'll go into a quieter period when I'll also get a different job. So you can see this multi-decadal variability going back quite far. Here's a number of major hurricanes in the Atlantic all the way back to the start of the 20th century. Now, when you start going back into these earlier periods, you have to realize that a lot of these systems may have been underestimated or missed completely due to the fact that we had very limited observations in the eastern part of the Atlantic basin. Prior to the mid-60s, we had no satellite data, and prior to the mid-40s, no aircraft reconnaissance. So systems in the eastern part of the basin may have either been underestimated or missed completely. But if you look in general, you can see an active period since 95, quiet from 70 to 94, active from 26 to 69, and then quieter from 1900 to 25. Now, if you look at historical data and you look at landfall data, the 1970 to 94 period is almost unusually quiet, even from a longer period historical data set, that the 70 to 94 period is very, very quiet compared with even longer period records that go back all the way to the 1600s. So we were in a very quiet period from 70 to 94, and Dr. Gray likes to remind me that during that time period was when he was really doing a lot of his research. He was trying to get grant funding, and there wasn't a whole lot of grant funding in the Atlantic simply because there weren't very many storms to worry about. So this thermohaline circulation tends to fluctuate on these multi-decadal timescales. Basically what happens is when the circulation is going strongly, you have high salinity content water that's being depleted in the far North Atlantic faster than it can be built up in the subtropical highs. And over time, the circulation kind of discharges the high salinity content, and over time the circulation weakens. The salinity drops to a level where you really don't get as much deep water formation, and you go into when the circulation is weak. Then when the circulation is weak, the salinity begins to build up, eventually reaches a place where it's strong and high enough salinity where you can get deep water formation again. So overall, this is why we believe the thermohaline circulation fluctuates on the time scales that it does. And again, it's not just the water temperatures in the Atlantic that cause changes in this Atlantic multi-decadal oscillation. You get warmer water temperatures, but when you have warmer water, you tend to have lower pressures, more moisture, weaker trade winds, reduced vertical shear. All of these conditions tend to be very strongly correlated. Overall, a more unstable environment and more favorable wind conditions that typically relate to more active hurricane seasons. So consequently, it's all of these fluctuations going on together that cause the changes in hurricane frequency and intensity that we observe with a positive phase of the Atlantic multi-decadal oscillation or a strong phase of the thermohaline circulation. Now, we've been very fortunate in recent years, and we don't really necessarily believe that that's going to continue. For example, if you look at the schematic here, from 1949 to 1966, during those 18 years, we had a total of 16 major hurricane landfalls. So nearly 0.9 landfalls per year, and about a quarter of all the storms that reached major hurricane strength made landfall in the U.S. at major hurricane strength. So about a quarter of them did. Then if you go to the most recent active period from 95 to 03, during those 9 years we had 3 major hurricane landfalls. So only about 0.3 landfalls per year. And remember, before it was 25%. During those 9 years it was only 9%. And we were pretty fortunate even in those 3 major hurricanes. One of those was Brett in 99, which made landfall in the King Ranch area of Texas, where not very many people live, and it did very little damage. Obviously, if it had made landfall either in, say, Brownsville or Corpus Christi, the damage would have been much higher. Obviously, then we had 04 and 05, 3.5 landfalls per year, and we had 54% of all our storms make landfall as major hurricanes. So we were very unlucky during those 2 years. But then since then, we've actually had no major hurricane landfalls. During 7 years, we've had no major landfalls, and we've had 22 major hurricanes during that time period. Now, obviously, Ike was a very strong Category 2 and did a huge amount of damage, and certainly Sandy was an unusually large hybrid system that did an extensive amount of damage. But from a pure meteorological perspective, we've now gone 7 years with no major hurricane landfalls. Now, if you look at historical data of landfalls, it goes back reasonably well to the late 19th century, since generally the coastline was reasonably well populated during that time. If you go back to 1878, we've never had a 7-year period with no major hurricane landfalls. So from that perspective, we've been very lucky the last 7 years. And just to show we've been incredibly lucky along the Florida Peninsula and East Coast, even going back further. For example, from 1919 to 65, we had 26 major hurricanes in 47 years. During the most recent 47 years, we've only had 7 major hurricanes, so nearly only a quarter as many. So again, we've been very lucky from a major hurricane landfall perspective, especially along the Florida Peninsula and the East Coast. Obviously, if we were to get storm formation or storms recurring at the rate that they did during this earlier period, we would expect huge amounts of damage, because obviously there's a lot more people and a lot more population in harm's way than there was in the 40s, 50s, and 60s. Again, just because a lot more people live along the coastline than did during that earlier period. So the question is, well, why have we not seen any landfalls the past 7 years? And the primary reason why we think that's the case is because we tend to have a trough of low pressure along the East Coast. And with this trough, you tend to get a flow around this trough that basically pushes storms towards the north, and then as they reach let's say around 40 degrees north, they hit the latitudes of the jet stream, and then they recurve and move out to the east, bypassing the U.S. coastline. And we tend to have this trough of low pressure the last 7 years, and this trough has basically been one of the primary reasons why we haven't seen major hurricanes making U.S. landfall the past 7 years. Now, this is an average pattern. Obviously, you do get ridges during these time periods, and it's just a matter of having a ridge over the eastern U.S. at the same time as the storm is approaching to really get a U.S. landfall. That's kind of the pattern that we had with Sandy. I'll talk a little bit more about Sandy in a couple of minutes. Now we'll move in and talk about the 2012 hurricane season. Obviously, 2012 was a very active hurricane season from the number of named storms, but it was actually very quiet when you look at the number of major hurricanes. Overall, the season had a total of 19 named storms. Of those 19 storms, 10 intensified into hurricanes, but only 2 reached major hurricane strength. Now, the average number of major hurricane days in a season is about 4. We only had half of one, and basically a major hurricane day is how many 6-hour periods that you have where you have storms that are at least at major hurricane strength. So an average season has about 4 of these. We only had half of one last year. So while it was a very active season for weaker storms, it was actually a very quiet season for the major hurricanes. Both of the major hurricanes barely reached major hurricane strength, and each did so for only 6 hours. Now there's a couple of aggregate measures that we like to look at to kind of help quantify the season better than, say, the number of storms. One of these is what NOAA uses, and that's this accumulated cyclone energy. Basically, accumulated cyclone energy, you take the wind speed at each 6-hourly interval when you have a tropical cyclone and you square it to approximate the kinetic energy. So basically an average season has about 92 of these units. Last year at 133. Net tropical cyclone activity is another metric that we like to use. Net tropical cyclone activity is basically these first 6 parameters, so named storms through major hurricane days normalized by their long period average values. So 100% by definition was the 1950 to 2000 average. The 1981 to 2010 median was 103%. Last year was 131%, so a little bit more active than the average season, but again, not as active as you would expect given the overall number of storms. Again, we had a lot of named storms, but not a lot of intense storms last year. Here's briefly some characteristics of 2012. You can see the tracks of all the storms. One thing that we didn't have a lot of last year was storms forming in the deep tropics. Say south of 20 degrees north, we only had 2 red lines, which means 2 hurricanes in the deep tropics last year. Again, we would typically expect a lot more of those in a season that had 19 storms. Last year we only had 2 hurricanes form in the tropics. And again, overall conditions were reasonably favorable. However, we saw a lot of dry air and a lot of stable air, which really suppressed these systems intensifying significantly. Now, briefly talk about Hurricane Sandy. I think the main takeaway point with Hurricane Sandy was that it was a giant storm. Here's kind of a forecast plot, but this shows basically just how large Hurricane Sandy was. If you look at the tightly bunched isobars, you can see the isobars from Sandy extend all the way from, say, the Tallahassee, Florida, all the way up into Newfoundland. So it was a massive system, and that's the primary reason why Sandy did all the damage. It wasn't that the maximum sustained winds around the center were that strong. It was just the system was huge, and with a very large system, you get a very extensive storm surge. Basically, what happened with Sandy was it formed in the Caribbean and then began to drift north towards the Bahamas. Then as it moved off the coast of Florida, it pretty much merged with a trough of low pressure. As the system merged, a high built in to its north, and the circulation around the high pressure area drove the low from southeast to northwest, which is a very unusual pattern. Typically you expect when storms reach about 30-35 degrees north, especially in October, they're likely to hit the jet stream and move from west to east. Last year it actually recurved, and actually didn't recurve, went back towards the west. And this was a highly unusual track, but it was actually well forecast by the global models. Especially the ECMWF model did a fantastic job. About 8-9 days in advance, it actually had Sandy forming and making that sharp westward bend towards the end of its lifetime and causing all the damage and devastation that it did. The main cause with Sandy was obviously it tracked into South New Jersey, and the circulation around the storm basically drove very strong surge along Long Island Sound and in northern New Jersey, causing extensive surge damage in the New York metropolitan area. The last insured damage estimates that I've heard are that it was about a $50 billion loss for the insurance industry. So one of the second most insured damage from a tropical or from a storm after Hurricane Katrina. Now, technically, I guess it doesn't quantify or qualify as hurricane damage, given that it would be classified as extratropical about 6 hours prior to landfall, but certainly it was still kind of a hybrid system, which is typically what you expect in this area anyway, is when you have systems in that area, they're going to be kind of a hybrid between a purely tropical system as well as an extratropical system. Again, Sandy was a very, very large system. My friend Brian McNulty put together an integrated kinetic energy estimate of how much intensity Sandy had. So this basically takes into account the maximum winds around the storm as well as the size of the storm. And you can see that while Sandy didn't actually have that strong of central winds, it was a very, very intense storm from an integrated kinetic energy standpoint, and certainly it had the second highest integrated kinetic energy, showing only Hurricane Isabel, which is another very large system that made landfall in North Carolina. Just to show, Sandy is not, while unusual, wasn't the only system to do something in a similar manner. Here's the tracks of 3 storms that made landfall in the New York City metropolitan area. We had landfalls in 1821, 1866, and 1893. Obviously, one of the big stories is obviously New York City is a lot more heavily populated than it was, say, in 1821. So the amount of damage is obviously much higher. But there have been other hurricanes that have impacted the mid-Atlantic. If you go back in historical data, you can see there were 6 during the 1600s, a few in the late 1700s, and then a few more in the 1800s. So while it was a highly unusual system, it was not unprecedented from tracks that other tropical cyclones and hurricanes have taken during the past. Overall, other characteristics associated with 2012, we had warm water temperatures in the tropical Atlantic. And while we didn't have El Nino last year, we had kind of warm neutral conditions. So neither El Nino nor La Nina, but more El Nino-like. We tend to have actually reduced vertical shear in the tropical Atlantic, which is enhancing for storm formation conditions. The big reason why we think 2012 didn't see more major hurricane formations was due to the fact that we had a lot of stable air and a fairly dry atmosphere last year that really kind of squashed the systems from really intensifying into major hurricanes. So now let's move in and obviously talk about 2013. 2013 is obviously the hurricane season started June the 1st. I'd say about 90% of all your hurricane activity occurs after the 1st of August. So we're really right now moving towards the peak of the hurricane season. All of our forecasts and our verifications are available on our project's website, which you can get at tropical.atmos.colostate.edu. So we have all of this information available on our website. With each of our forecasts, we put out numbers, but we don't just put out numbers. There's usually a 30 to 40 page document that goes out with each of these forecasts, explaining in great detail why we're issuing the forecasts that we are. So here's the numbers that we put out with our most recent forecast that came out on the 2nd of August. We're calling for a total of 18 storms, 8 of those 18 intensifying into hurricanes, and 3 of those 8 intensifying into major Category 3, 4, 5 hurricanes. Overall, if you look at the net tropical cyclone activity metric, we're predicting about 150% of the average hurricane season. Now, this forecast was put out on the 2nd of August, and we had already had 4 storms at that point. We actually had our 5th storm develop this morning, so our forecast is calling for an additional 13 more named storms. Here's the tracks of the storms that have already formed this year. You can see we have Andrea, Barry, Chantal, Dorian, and now Erin. The yellow crosses with Erin indicate where the storm is forecast to track by the National Hurricane Center. Erin has actually intensified fairly rapidly and is actually looking very healthy on the satellite imagery this morning. However, Erin's future intensity is a significant question. While now it's over relatively warm water and a pretty moist, unstable atmosphere, it looks like it's going to be moving into a drier atmosphere and a more stable atmosphere. The numerical models are pretty much calling for dissipation in about 3 to 4 days, while the statistical models indicate that Erin may maintain strong tropical storm or perhaps even intensify into a hurricane. So it'll be interesting to watch and see which of these 2 model camps is actually right. When it comes to forecasting track, dynamical models do a very good job of forecasting tracks of the storms, but intensity prediction is still a real challenge. Mark DeMaria, who works at Sierra at Colorado State, has actually been developing statistical modeling of hurricane intensity change, and these models and his statistical models do better in general than the dynamical ones. So it'll be interesting to see which one does better with Tropical Storm Erin. There is one other area that we've been watching, and that's near the Yucatan Peninsula. This area has been given a 50% chance of intensifying into a tropical cyclone over the next 48 hours. I think today it won't intensify anymore, just given the fact that it's going to be interacting with land. There is a potential for intensification once it hits the Gulf of Mexico. However, it looks like it's going to make a fairly rapid track, potentially northward towards the Louisiana coast. and if that track verifies, it could potentially be a mid-level tropical storm, but it could potentially drop a significant amount of rain in Louisiana and cause significant levels of flooding. Here's the forecast tracks for Tropical Storm Erin from a pile of numerical models. The official track is towards the low end, or towards the southern end of these forecasts. And some of these other models are more statistically based and don't have the same level of skill as some of the more numerical ones do. So the official track is to continue a west-northwest track towards the Lesser Antilles in 5 days. Obviously, the question with this storm in the Gulf of Mexico, or moving into the Gulf of Mexico, is how intense will it be? None of the numerical or none of the dynamical or the statistical models at this point forecast the system to intensify beyond tropical storm strength. So at this point, we don't think it's going to be a huge impactor from a wind perspective, but it could potentially drop significant levels of rain. So what's happened? We've issued another forecast in early August from our earlier forecast in early June. Our most recent forecast is a bit of a lowering from what we predicted in early June, and that's due to the fact that we've had some cooling in the eastern tropical Atlantic. You can see this is the difference in anomalies between late July minus late May, and you can see how these anomalies have cooled. The water temperatures have cooled, implying a more stable atmosphere than what we saw in late May. And we've kind of seen that stable atmosphere when we looked at some of the early season systems, especially Dorian, which formed in the eastern tropical Atlantic, intensified and then died off very, very quickly as it encountered a more stable atmosphere as it moved into the mid-tropical Atlantic. But while it has cooled a bit, the waters are still warmer than normal. This red box kind of highlights what's known as the main development region for tropical cyclones. And you can see that in general we have a lot of yellows and oranges indicating warmer than normal waters. So while the waters have cooled a bit compared with what they were in June, they're still above average and overall conducive for an active hurricane season. When it comes to the tropical Pacific, we have neutral conditions. We have kind of some yellows, some oranges, but overall conditions that we typically expect to see associated with neutral ENSO conditions. Vertical shear has actually been a bit stronger than normal from July through the early part of August. In the central part of the tropical Atlantic, we do expect these shear conditions to change given the fact that we have neutral conditions in the tropical Pacific, and we also have conditions over the Indian Ocean that would tend to make the atmosphere somewhat more La Nina-like and probably reduce the vertical shear compared with what you would expect even in a neutral year. Again, the atmosphere has tended to be a bit more stable than normal. This is a nice figure that's maintained again by the folks at CIRA, and you can see the atmosphere. The black curve indicates climatology, and you can see that the blue line has generally been below climatology, indicating a more stable atmosphere than normal during the 2013 hurricane season. And this more stable atmosphere, again, is unfavorable for hurricanes since hurricanes thrive off of deep thunderstorm activity. If the atmosphere is stable, you're less likely to get systems intensifying into tropical cyclones and into hurricanes. So the question obviously a lot of people want to know is, well, how are the storms going to track that form this year? And unfortunately, you can't say months in advance where the storms are going to go. That's governed a lot by day-to-day weather patterns. But what you can see from this is that we tend to have higher pressure along the East Coast from over the last month, which would tend to drive storms a little bit further west. However, obviously, these conditions can change from day to day, and what really matters when you're looking at storm tracks is, do we have a storm approaching the coast, and what is the overall track at that point? That's what's critical for whether storms are going to make landfall on any particular day. So we are pretty confident we are going to see neutral conditions for the remainder of the hurricane season. The ECMWF model, which is generally considered one of the best numerical models, is in general calling for La Nina or neutral conditions for September and October. This is its ensemble forecast. The ECMWF has also tended to be forecasting conditions warmer than what we've seen since the start of the year. So in general, we think El Nino is not likely to play a role with this year's hurricane season. There's a whole pile of numerical and statistical models that issue El Nino forecasts, and none of them are forecasting El Nino conditions for the August through October period. So overall, we think cool neutral conditions are probably our best bet for the remainder of the hurricane season. So with our forecast, we issue a statistically based prediction, which would be based on historical data and how well these predictors would forecast hurricane seasons in the past. And we use a new reanalysis data set which provides globally gridded data back to the late 1970s. This globally gridded data set seems very accurate and based for historical storms or for historical data, and consequently that's what we use to come up with our statistically based forecast. You can see the forecast shows significant levels of hindcast skill, so how well this forecast would have done on historical data. From 79 to 2012, you can see the forecast in general matched the observations quite well. The correlation is above 0.9, indicating that these forecasts explain over 80% of the variability from climatology. So a very skillful hindcast scheme. Now obviously one of the big things is, well, a hindcast isn't a forecast, and that's very true. But however, this forecast actually did do reasonably well last year. As you can see from the final line here, the forecast did reasonably well last year. And overall, we're relatively confident the forecast will hold up reasonably well this year. We also select analog years, which are years in the past that had conditions similar to what we currently see. You can see the average of these 5 analog years had about 140% of the average hurricane season when looking at NTC, and our final forecast is close to the average of these 5 analog years. We put out 4 forecasts each hurricane season. The first forecast is in early December, and in this forecast we don't put out numbers. There's really no skill that far in advance. What we do in early December is we put out a discussion about what features we think are likely to play a role for the upcoming hurricane season. Then we put out 3 qualitative or quantitative forecasts, one in early April, one in June, and one in August. Each of these forecasts, we use a statistically based model, and the forecasts tend to improve and get more skillful as you approach the peak of the hurricane season. And again, that's to be expected because obviously when you are issuing forecasts, as you get closer to the events that you're trying to predict, your forecasts generally have more skill. As an analog, you can think about forecasts for tomorrow's weather tends to be a lot more skillful than the forecast for the weather a week from now. Now, you can't say months in advance when or where storms are going to strike, but what we can say is that in general, more active seasons tend to have more landfalling hurricanes. So these are the probabilities for each area along the U.S. coastline experiencing a major hurricane this year. The numbers in parentheses are the numbers based upon historical data, while the numbers to the left are the probabilities based upon the current forecast. And you can see that in general, the probabilities this year are well above their long period averages because we're forecasting above average hurricane season. So you can see, for example, with the entire U.S. coastline, the probability of a major hurricane this year is 64%, compared with the long period average, which is 52%. And likewise, you can see the other probabilities on this slide as well. Again, we do probabilities for various areas along the U.S. coastline, all the way down to the state and even the county level. You can access all of this landfall information available on our partner website, which I put together in partnership with the Geographics Lab at Bridgewater State University, which is also my alma mater from undergrad, so go Bears. But the URL you can access here, it's www.e-transit.org/hurricane. You can also access these particular websites off of our primary website, which is the tropical website, which I provided at the start of this talk. So we have probabilities at the state level. These are the probabilities of each state being impacted by a storm in any particular year. You can see, for example, how high the probability is for the state of Florida. And that's to be expected for a couple of reasons. First of all, the state of Florida obviously gets hit by a lot of storms, but also the state of Florida is very large from a coastline distance perspective. And consequently, since it's a very large state, it has a large amount of coastline that's likely to be impacted. If a storm makes landfall in Florida, it's no guarantee that the entire state of Florida would be impacted by the storm. However, if a state like Mississippi were to be hit by a hurricane, certainly the entire coastline of Mississippi would be impacted by the storm simply because there's a lot less coastline in Mississippi than there is in Florida. So you need to take this kind of information into account when looking at the probabilities of each state being impacted by a tropical cyclone this year. We also provide probabilities of each island in the Caribbean being impacted by tropical cyclones. Again, the numbers in parentheses are climatology. The numbers for 2013 are to the left. For example, the country of Haiti, the probability of a hurricane impacting Haiti this year is 36%, compared with the long period average, which is 27%. Obviously, in the case of Haiti, one of the big concerns is that it doesn't even take a hurricane to cause significant levels of damage in Haiti, simply because obviously a tropical storm or even a tropical depression can cause significant levels of damage in Haiti just due to the intense rainfall and mudslides that are typically associated with tropical cyclones in this area. So now let's finish by talking about 2-week forecasts in the Atlantic Basin. We've been putting these forecasts out since 2009. These forecasts have been put out basically because you can have active periods during an inactive season or inactive periods during an active season. 2008 is a prime example of this. In 2008, it was a very active hurricane season. It was Hurricane Ike. We had 5 major hurricanes that year. But from September 2nd to September 25th, which is the climatological peak of the Atlantic hurricane season, no storms formed. So you had a very active hurricane season and the most active period of an active hurricane season, and no storms formed. So the question is, what kinds of things are going on there to cause these types of alterations in storm activity during the peak of an active hurricane season? And we had some ideas, but it seems like it's primarily due to the alterations in strength of the Madden-Julian oscillation. Now, if you're in that weather and you come up with an oscillation, you're good to go. Your grants get funded and everything else. So I'm still looking at the how to figure out the Klotzbach oscillation. But this Madden-Julian oscillation, what it does is it alters levels of tropical thunderstorm activity around the globe. And as it does so, as these deep thunderstorm activity propagates eastward, it alters upper level and lower level winds. And that's the primary reason why we believe that this MJO impacts storms in the Atlantic. When it's located in the Indian Ocean, you get reduced westerly wind anomalies at low levels and upper level easterly anomalies, which reduce your vertical shear in the tropical Atlantic. Well, overall, when you have these type of wind anomaly patterns, it reduces your vertical shear. So you can overall think of it basically as mini El Nino La Nina on a subseasonal time scale. So when this Madden-Julian oscillation is strong, it does provide for significant levels of predictability. Now, this Madden-Julian oscillation is able to be monitored in real time, and you can see basically where it is at any particular time. This just shows the propagation of it from December through January. When it's located in phases 1 and 2, primarily in the Western Hemisphere and over the Indian Ocean, you tend to get reduced vertical shear in the Atlantic, and overall you just end up with conditions that are more conducive for storms to form in this area. Now, these 2-week forecasts have worked out very well last year. We basically issue a 3-year forecast, either below average, average, or above average. And our forecast last year verified in the correct category 5 out of 6 times. And we issued our first 2-week forecast back on August the 2nd, and we predicted below average activity. And that's going to verify quite well. Today's the last day of that 2-week period. And to this point, we've only had 1 storm form, and it's generated very little ACE so far. So the forecast, our first forecast, which is 2013, is also going to verify in the correct category. So with that, I'd like to thank you very much for your attention. And I'd like to finish with an admonition from Arago, who was a French scientist during the 19th century, who stated that never, no matter what may be the progress of science, will honest scientific men who have regard for their reputations venture to predict the weather. So with that, I'd like to thank you very much for your attention, and I'll try to answer any questions that you may have, and now I'll turn it back over to Henry.
Thanks, Phil. Boy, some really interesting stuff there. We learned a lot from your presentation. We're going to take questions now. If you guys have any questions, go ahead and type them in. We'll try to answer those. Nolan, are you there in the background? Do you have any questions for Phil? Start off.
Phil, what was the first hurricane you remember?
That's a good question. I think a lot of people that study hurricanes, there was kind of one hurricane that really got them interested in storms. And as Henry mentioned, I grew up in Massachusetts, so we aren't hit by a lot of hurricanes. But 1985, Hurricane Gloria came through Connecticut and caused quite a bit of heavy weather back in Massachusetts. And I was pretty fascinated by how a storm could be so powerful and do all that damage. So Hurricane Gloria is really the one that got me interested in storms. And then Hurricane Bob a few years later in 1991 kind of helped to buoy that interest, and ever since then I've kind of been a certified weather geek, I guess.
And I'm, having grown up in central Illinois and then moved west to Colorado years ago, I have never been in the path of very many hurricanes, and I never caught the hurricane fever that so many meteorologists do.
Phil, a question I remember before I moved out here to Colorado, always thinking, Colorado, that's a strange place to study hurricanes. What brought the program out here? Why Colorado State University?
Well, that's a good question, and that's true. And Dr. Gray and I always give the answer, well, the storm surge can't get you at 5,000 feet. But one of the primary reasons why was the guy that started the Department of Atmospheric Science in the early 1960s was a guy named Herbert Reel. And he was a renowned hurricane scientist who actually had been based at the University of Chicago. Again, Chicago is not really anywhere near hurricanes, but pretty much he came out here to start the department, and about the same time he came out, Bill Gray was one finishing off his PhD at the time, so he came out with him. And I guess it kind of started with those two guys since they were pretty good, since they were pretty big in the hurricane field, and it's kind of stayed that way since that time. We've had a lot of other hurricane professors and hurricane scientists at CSU, and obviously with the technology that we have today, you don't need to be really in Hurricane Alley to be able to study hurricanes.
Okay, we're going to start taking a couple of questions. We've got one here from Braden in Colorado. We want to know what current changes in the Atlantic can or are impacting the duration of the thermohaline circulation. Is it known if polar ice crystals influence the migration of deep water?
That's a good question. We don't think, say, on they've done a lot of studies looking at how much the thermohaline circulation would weaken if they, say, had a significant melting of polar ice caps and things, and there really doesn't seem to be too much there. We do actually have a pretty significant number of floats now, a number of buoys. There's been a big effort to try to measure basically measure salinity and temperature in the Atlantic. So I think in terms of being able to predict when the thermohaline circulation is going to weaken the next time, you may actually have a little bit more headway so I can get my job search started. But no, seriously, actually, besides that, there are a lot of other things that are related with this thermohaline circulation. The tropical Atlantic cools, the far North Atlantic cools, and you tend to get a whole lot of other things that change, atmospheric conditions that change. You tend to get more frequent and stronger El Nino events. So if you know a couple years in advance that these changes are happening, you can start planning for some of this action. Another major factor is that when you have a weaker thermohaline circulation, you tend to get pretty significant droughts in West Africa, which again, obviously in that area is kind of, it has a marginal economies to begin with. So if you know droughts coming, potentially you can help with some of that as well.
Okay, Ted from Missouri writes in and that he says he's noticed, or he wants to know that what causes precipitation differences, and this is not tropical stuff, but Missouri, they've had severe weather, reports less than a mile away, not so much. He's wondering, you mentioned wind shear. Does that have anything to do with storms and stuff on the continent affecting how much rain falls?
Yeah, I mean, wind shear is, I was actually down in Australia for a few months back this past winter doing some tornado research, and it's interesting because kind of being a hurricane guy, you think about shear as being detrimental for storms to form. But when you're talking about mid-latitude storms, those actually tend to thrive in high shear environments, especially tornadic activity. You need lots of shear to create and generate the spin that you get and the rotation that you need to get those supercell thunderstorms. So yeah, in general, if you have a lot of shear and you have enough moisture and other lapse rate conditions and such are correct, you can actually get significantly enhanced precipitation and stronger supercells with stronger shear. So shear is detrimental for hurricanes, but in mid-latitude weather in general, stronger shear can often generate is generally responsible for generating the stronger supercell type events.
Okay, Ralph writes in and he wants to know, is there any scientific reason why Northeast Florida seems to be so lucky from getting direct hits from these tropical systems?
Well, that's a good question. I think one of the primary reasons is just due to the way that the coastline is shaped. I guess we can go back and look at that here. Let's see. If you look at the state of Florida, that's not a great map. Let's see if I can find a better map here. The state of Florida tends to basically kind of curve in. So it tends to stick out a little more towards the south and then curve in a little bit more towards the north. So usually storms, as they move across the basin, move from east to west, and then as they reach the coast of Florida, they start to tend to gain latitude and move towards the north. So to really get into, say, northeast Florida and Georgia, it has to take a kind of an unusual track. Now, we have seen some storms do that, but it is a fairly unusual track, and I think one of those reasons, again, why northeast Florida doesn't get hit is that simply just the way that the coastline is shaped, it's less likely to be impacted than, say, either the North Carolina coast that, again, sticks back out into the ocean, or South Florida. The North Florida, it has taken a somewhat unusual track to get up in there.
And you know, John writes in too. His question was, how exposed are the Florida Keys to major storms? And I think you're pointing that out right here, that they're sticking right out there.
Yeah, exactly. The Florida Keys certainly. Well, and obviously the Florida Keys, the big challenge is you have no place, because a lot of times you want to basically, if you can avoid, you don't really want to evacuate the area. In general, if you can, especially the surge, you basically want to just get above it. But obviously in the Keys, there's really no place to get above it. So obviously you have to get everybody off the Keys, which is a really hard proposition because you have one road out.
Okay, here's two questions that are pretty similar. Stanton writes in, what is the relationship between your products and those of NOAA? Do they complement, supplement, or serve as alternatives? And then I have another one here from Cindy wanting to know, does the Colorado State forecast differ from the one put out by the National Hurricane Center? What factors, what different factors, I guess, do you input than that they have? So two questions kind of similar.
Yeah, well, yeah, I mean, the Hurricane Center and NOAA, that's the same, just to clarify, those would be the same forecast since the Hurricane Center is part of NOAA. And our forecasts generally are quite similar in that basically the couple of the forecasters that are at the Hurricane Center came from Bill Gray, so they obviously kind of look at things the same way that we do. And there's certain large-scale conditions that everybody who does statistical prediction looks at. The differences, I would say, are the Hurricane Center uses a few numerical models that we don't have access to. So they do have a little bit of a dynamical bent in their forecasts. The other difference, I would say, is that our forecasts, in terms of what's actually online and what's actually available with the forecast, ours are a lot more extensive. We go into a lot more detail describing the forecasts. The other difference, I guess, is our forecast is one number and theirs is a range. Now, obviously, we understand that with our forecasts, you can't just predict one. I mean, you predict one number, and that's kind of your best guess, but you obviously understand there is some uncertainty. So in the forecast itself, we do put in kind of a range and error bar in there, so you kind of have an idea, based on historical errors, how many storms you would expect kind of the range to be. But when we put out the forecast itself, we just put out one number. And I think a lot of that is because if you put out a range of numbers, often the media will just grab the high number and do things like, for example, I know when I was down for a conference, NOAA came and put out their forecast, and I think they predicted 6 to 10 hurricanes. So the media grabs it and says up to 10 hurricanes, which a lot of times the public will interpret as 10 hurricanes. So I think sometimes if you give them one number, at least as long as they copy and paste that number down correctly, you at least get a better kind of interpretation of what you're actually saying.
Thanks. Here's another one. This is from Kristen, and she says, does the presenter's model address long-term changes in hurricane number and or intensity related to climate change?
Well, that's a good question. We really haven't. I think the long-term trends that we see in the Atlantic are primarily due to improvements in observations. Basically, if you look at the number of storms, that's gone a lot higher in the last, say, 10, 20 years. But I think a large portion of that is due to the fact, similarly with tornadoes, the observational network that we have is much improved. We have a lot of microwave data, so a lot of these marginal systems that are being named now that probably would not have been named even 20, 30 years ago. When you look at the more intense storms, we really actually haven't seen much of an impact of climate change on hurricanes. While we've seen climate change impact a lot of other areas, we really haven't seen much of an impact on global tropical cyclones. In general, the Atlantic tends to go opposite of the other basins that have tropical cyclones, like the Western Pacific and the Eastern Pacific and down by Australia and the Indian Ocean. So if you look actually at globally at tropical cyclones and look at that ACE metric that I talked about earlier, and you look at global ACE is actually at about a 30 to 40-year low right now. So while climate change has certainly impacted a lot of areas, we really haven't seen much of an impact, at least yet, on tropical cyclones.
Okay, thanks. Here's one from Willard wants to know, was Sandy a major anomaly, or are there possibilities of this type of storm in the future?
Well, I mean, it certainly was an anomaly, but again, I mean, it happened once, it could happen again. I mean, it's one of those things where it was basically a combination of a very large hybrid system, which you do get on occasion, but it's actually taking a very unusual track. I think the track of Sandy was more unusual than, say, the fact you had a very large system off the east coast of the U.S. I mean, you do get those from time to time, but often if you get one off the east coast, usually they end up recurving and maybe going and impacting George's Bank in Newfoundland. That's a lot more typical track than, say, one that backs in towards the west. So I think that was really the thing with Sandy. It wasn't that it was the intensity of it was so strong. It was more just the unusual track that it took. So it's hard to really quantify. I know I just saw a paper that came out trying to kind of estimate the return period of a Sandy-like storm. And they estimated it somewhere around, like, I believe 1 in 300 years. So again, it's hard to estimate given the fact that until last year we hadn't had a storm quite take the track of Sandy. But based on statistical modeling and things like that, I guess you could say it's, you know, a highly unusual event, but something that we certainly could see again. And obviously, as more people move to the cities and as you know, people have more and more stuff in harm's way, they're just going to progressively do more and more damage.
Okay, Phil, here's another question. Do you guys do forecasts for the Hawaii Pacific areas as well?
No, we don't. We just do the Atlantic. The Eastern Pacific Ocean, the Hurricane Center does a forecast for the Eastern Pacific. That does, I believe, include Hawaii. And also, when there's individual storms tracking near Hawaii, that's actually covered by the Central Pacific Hurricane Center, which, again, is part of NOAA, but is a slightly different organization from the National Hurricane Center. And then for other basins, actually, there are some numerical modeling groups that do them, and also there's a group out of Tropical Storm Risk out of the UK that does forecasts for the Western Pacific.
Ralph writes he wants to know, with some models he noticed in the forecast tracks were way out there, they were way off, and he wanted to know, why are they still being used if they're not accurate?
Well, that's one of the things is obviously on an individual storm basis, you may have one model that's completely out to lunch. And just a lot of that comes with the weak storms just because it's not, they don't initialize them. Sometimes the model isn't initialized very well. Some of the models also, that's my friend Jonathan's website, and basically that's all the guidance that they use. A lot of those are kind of basically beta and advection model, which basically is just being pushed by the current, basically being pushed by the current conditions and not taking into account anything changing in the future. So those are kind of like your no-skill models, but in terms of what's actually the Hurricane Center looks at, they might look at those, but in general, unless it's a very, very shallow system, they tend to be steered by higher level winds. So they'll look at those models a little bit, but in general, when they look at forecasts, they're pretty much using the numerical models purely for their track guidance.
Okay, Cindy writes in, and she wants to know, does your website have historical data for hurricanes before the 20th century? If not, where can she find that data? And let me make a point here that we're going to ask Phil to send us a list of his links that he's gone through on this. If you can do that, Phil, we'll post those on our website for folks to go to for the different ones you highlighted there. So this question, before the 20th century.
Yeah, I don't actually have the, I mean, I have a couple like spreadsheets with some of the data tabulated that I assume you'll provide my email address at the end. So if you're interested in some of that data, I can happily send it to you. All the data I have, I've gotten from the National Hurricane Center. So the National Hurricane Center is pretty much the kind of the purveyor or the group that maintains all the historical hurricane data for the Atlantic. So if you go to their website, which is nhc.noaa.gov, and you go to, like, I believe it's like climate or archive data, you can get access to all these historical data. Just keep in mind that storm data prior to the 20th century, while landfall data is probably reasonable since there were people living along the coastline, once you start getting the basin-wide data, there's a lot of uncertainties. There's basically no storms in the Eastern Atlantic because there was no aircraft, no satellite, and ship traffic generally tried to avoid hurricanes if at all possible.
Lisa from Indiana writes in, and she noticed that, you know, that with the heavy precipitation, a lot of places have sinkholes developing. And is this any cause and effect there with from hurricanes?
I don't know particularly. I mean, I would think in general sinkholes form in areas where you have obviously a very, very wet soil. So if there had been tropical cyclones that had made landfall and dropped a lot of rain, that could potentially cause a little more significant, or cause a potential for mudslides or potentially for sinkholes to develop. I know the East Coast, you've seen a few more of those recently, and that's because the East Coast generally had a lot of rain, but it hasn't really been tropical cyclone related. We haven't really had too much in the way of tropical cyclone impacts this year, other than I believe it was Andrea early on did dump some rain, but in general it's just been a pretty wet summer along the East Coast of the U.S.
And sometimes the sinkhole formation is when groundwater extraction has in fact removed water from beneath. So it's a complicated system and probably not that related to tropical cyclones.
Here's a question that the viewer wants to know: does the MGO process around the globe progress around the globe from one hurricane forming basin to another, and how long does a full circuit take?
That's a great question. I actually just published a paper, or not published, I wish it had been published. I just submitted a paper for publication that actually shows that is pretty much the case, that when this Madden-Julian oscillation propagates around the globe, as it does so, it'll alter storm activity in one basin and then in another. And this actually, I'm not the first person to observe that storms tend to cluster. Dr. Gray back in the 70s wrote a big, long paper showing how storms clustered in time. And what you'll find is that, for example, you'll get the MJO tends to trigger in the Indian Ocean, so you'll find when it does so that you'll get storm formation enhanced in the Indian Ocean, and then it'll enhance in the Northwest Pacific, and then in the Northeast Pacific, and then in the Atlantic. And a full circuit of the Madden-Julian oscillation typically is about 40 to 50 days. Sometimes it can be as fast as 30 days, and other times it can be as long as 60 days. The Climate Prediction Center of NOAA actually has a nice monitoring website where you can see where the MJO is on any particular day, as well as forecasts from various numerical models as to how it's going to propagate.
Jan wants to know, she states that amazing progress has been made in forecasting the direction of storms. What's the prognosis on intensity forecasting?
That's a good question, yeah. I mean, I think the thing is, with track of storms, a lot of the forecast with track is basically just being able to predict the large-scale steering, which basically is mid-latitude and tropical weather, which is pretty predictable out 5-7 days now. The challenge with intensity forecasting is that you've taken into account a process that we really don't completely understand exactly why storms intensify yet. And also you have to take into account kind of external factors, so the environment around the storm, the shear of this around the storm, the moisture processes, things like that. But you also have to take into account the internal structure of the storm. For example, hurricanes will go through eye wall replacement cycles where basically you'll get a secondary eye wall or a secondary air deep thunderstorm activity that will form and eventually will choke out the inner eye. These processes are still not particularly well predicted, but they can cause significant weakenings of a storm followed by re-intensification a little later. So being able to forecast all these processes is very complicated. So I think that's why, while we've had really fantastic improvements in track prediction, intensity prediction really hasn't improved over the last 20 years. I think that's primarily just due to the fact that we're working with a very, very challenging, it's a really challenging problem to solve.
Okay, looks like our last question here for the day. I guess Eddie came in late. He wondered if you could quickly review the outlook for the South Atlantic for the remainder of the Atlantic tropical season. If you could just quickly get a couple words.
Sure, I assume you mean the North Atlantic.
Right, I guess, yeah. He's
okay, yeah. I would say the South Atlantic is we've only had one storm back in, what was it, 2004 or whatever, like Catarina storm, and there may have been a couple in the 1800s. But yeah, the North Atlantic, we're predicting an above average remainder of the hurricane season. Let's go back and let's pull up the numbers. The total forecast is for a total of 18 storms, 8 hurricanes, and 3 major Category 3, 4, 5 hurricanes. Our forecast is basically due to the fact that we expect the Atlantic is a little bit warmer than normal, and we expect to have reduced shear for the remainder of primarily for the remainder of the hurricane season. I'll give you guys a little bit of a sneak peek to those that are still listening. I will put out my new 2-week forecast tomorrow, but I'm going to be going above average for the next 2 weeks, given the fact that overall, obviously, we have a storm or two that look like they're going to form, And we also, the Madden-Julian oscillation will be moving into phase 1 most likely. Most of the models are predicting that. And when the MJO is in phases 1 and 2, tends to be when overall storm activity in the Atlantic, that's when you get your most storm activity forming and intensifying in the Atlantic. So that's basically what my forecast will be for the next 2 weeks. So you guys get a little bit of a sneak peek on that one.
You know, Phil, I guess I misinterpreted Eddie's question. He had SAL. I was thinking that was South Atlantic. The Saharan air layer is what.
Oh, okay. Sure.
Okay.
Yeah.
So there we go. That's what it is. Want to know what the outlook for the Saharan air layer?
Yeah. The Saharan air layer, typically from a climatological perspective, it tends to weaken. You get a lot of dust in June and July, and then once you get into August and September, you don't get as many dust outbreaks. We had a very strong dust outbreak about 2 weeks ago, and I know there was a lot of talk about that. However, it seems like those dust outbreaks have become a little bit less frequent and a little less intense the last couple of weeks. So overall, I would expect that the Saharan air layer probably won't be playing as much of a role, especially once you get into September. It often doesn't play as much of a role. But overall, right now, the atmosphere is still a little bit more stable than normal. And that's what we see even with the forecast for Aaron, that while the storm is forecast to intensify for a couple of days, after that point it may actually start to weaken, given the fact that it's going to be moving into a more stable atmosphere. So I think one of the big take-home points is that we have dynamical conditions, so shear conditions and low-level spin conditions that are favorable for storms. The moisture and stability things have been a bit unfavorable for storms, so it'll be interesting to kind of see how those two things play out for the rest of the season.
Okay, we've had another question pop up. This will be our last one of the day. Since the moon affects the tide, what role does it have on hurricanes and stuff when it's full?
We really haven't seen too much of an impact, except as you mentioned with the tide. So if you have, say, at new or full moon when your tidal range is larger and the storm were to make landfall at high tide, it could potentially have a higher surge impact due to that. But that's pretty much the only impacts that we see would be, say, on storm surge at landfall.
Well, Phil, thank you for a great presentation today. Nolan, any last comments?
No, thanks a lot, Phil. We appreciate you taking the time.
Yeah,
Sure,
hopefully
no problem at all.
Next time you're in town, stop over and visit us. We're great to catch up with you. So again, thanks again for having us today and or being with us today. Well, we want you guys out there as you leave the webinar today to fill out that survey if you can, and please join us for our next CoCoRaHS WxTalk webinar. That'll be on September 12th. So mark your calendars. We'll have a registration for that open soon. It'll feature a former AMS president, Walt Lyons, currently with FMA Research, and Walt will speak about the 100th hunt for the red sprite. So all about sprites. Those are the strange lights folks have been seeing for centuries in the night sky above thunderstorms. He's done a lot of research on that. So it should be a great webinar there. Again, thank you again to Phil, and thanks, folks, for being with us this afternoon. We hope you have a good week. We'll see you next time. Bye-bye.